Alright guys, so we're going to continue on with our next lesson. For the first part of this lesson, I'm going to go through these problems that are review problems from the previous function operations lesson. So if you want to try these first, pause the video, and then you can unpause it and listen to the solutions. So on number 1, I'm taking f of x plus g of x. That means I'm adding function f plus g. I'm going to zoom in here to make this a little bit bigger on the screen. But I'm going to take x squared minus 2, that is f of x, and then I'm going to add that to g of x cubed plus 4x. If I add those together, remember adding just means collecting like terms. Notice that there's not really any like terms. The only thing that I can do here is put them into what we call that standard form, where I start with the highest exponent and I work my way down. X cubed plus x squared plus 4x minus 2. The domain, remember, is the x values that you can plug into this function. This is a cubic function. Remember to think about what a cubic looks like graphically. It's that kind of tall sort of S shape, not like the flattened out S shape of a cube root. It is a cubic function, and it's going to eventually touch every x value. So this one would be all real numbers. And again, remember, you can write out the words all real numbers if you want. Number 2, f of x times g of x. You take x squared minus 2 times x cubed plus 4x. Notice on this one, you are multiplying, so you'll be using the FOIL method. X squared times x cubed. That's x to the 5th. X squared times 4x. That's 4x cubed. Negative 2 times x cubed. Negative 2x cubed. And then negative 2 times 4x. That's negative 8x. Those two terms in the middle are like terms. 4x cubed minus 2x cubed is 2x cubed. Remember, when you're subtracting and adding, you don't do anything weird with the exponents. Different when you're multiplying. This one is a quintic function. Notice it also is going to be all real numbers that you can plug in for x. The next one, you have f of g of x. Remember, that's how you say this. This is a composition of functions, we call it. But you're taking f of g of x. So you are going to essentially plug in. Oh, that's not going to work for me, is it? Let's try this a different way here. No, still not going to work for me. All right. Let's see if we can get it to slide one at a time here. I apologize for that. Could have went the easy route first. I was trying to be too fancy with it. Remember, f of g of x essentially means I'm taking the function for g of x, which is x cubed plus 4x, and plugging it into f of x. So instead of x squared minus 2, I'm going to put a parenthesis squared minus 2, but instead of x, I'm taking this function right here and plugging it into that x. So I'm plugging x cubed minus plus 4x, into that. Now what that does require is that I do x cubed plus 4x times x cubed plus 4x. So this one's going to be a little bit uglier to multiply. X cubed times x cubed is x to the 6th. X cubed times 4x is 4x to the 4th. 4x times x cubed is another 4x to the 4th. And 4x times 4x is 16x squared. So then you add your like terms. 4x to the 4th and 4x to the 4th is 8x to the 4th. The 16x squared stays there, and then the minus 2. This one is degree 6. Remember, we didn't name anything degree 6, but it's still a polynomial. It's still going to have all real numbers that you could plug in for x. The final question of our little warm-up and review here is g of x divided by f of x, which means x cubed plus 4x divided by x squared minus 2. Now, what you should notice, hopefully, is that on the top of this, I could take that x and factor out an x and get x squared plus 4 left over. On the bottom, though, I cannot factor it. So if you don't remember, you need to go back and watch the other video that I made. I told you that for something to cancel out on the top and on the bottom, you must have the exact same factor on the top and on the bottom. Those are not going to cancel because it's not the exact same factor on the top and on the bottom. So there's nothing that cancels out here. So this is simplified. And we're going to talk about that in a lot more detail when we get into the chapter on rational functions. The domain, though, is critical to pay attention to when it comes to a fraction like this. The bottom of this fraction cannot be 0. So that x squared minus 2 on the bottom cannot be equal to 0. But basically, if you look at this little equation right here, even though it's not truly an equation, it has a little not equal, you can solve it like an equation, and you can actually find the answers that cannot be x. Because if you don't want it equal to 0, just set this little thing up like this, not equal to 0, and you can add 2 to the other side. Take the square root. Don't forget your plus or minus. So the square root of 2 is not a perfect square, so you can leave it as the square root of 2. That means that x cannot be positive square root of 2 or negative square root of 2, because that would make the bottom of the fraction be 0. Now what that's going to cause is kind of some weird stuff on the graphs later on when we talk about those. We're not talking about those right now, so all I need you to know right now is that you need to watch out and make sure that you don't plug in something that makes the bottom of a fraction equal 0. Okay, so our topic for today is on inverse functions. Now, we are going to take a look at something that goes back to way back in the early part of the year, in the first 9 weeks. We learned a definition of this thing called a relation. We also learned the definition of something called a function, and we'll talk about that in a little bit more detail here in just a second. Basically, what a relation is when you have inputs that are mapped to or give you outputs. So I'm going to write these tables sideways just because I didn't leave myself a ton of vertical space here. So we're going to go and we're going to say -2 for x, 0 for x, 1, and 3. And I'm just making these numbers up, by the way, in case you wanted to know. I am not getting those from anywhere in particular, just making them up. So let's say we have -2, 4, and then we have 0, 2, and then we have 1, 1, and then 3, -4. I don't know, I'm just making up some numbers again. This is called a relation. A relation is when you have a set of ordered pairs, inputs and outputs, inputs and outputs, inputs, outputs. Those are ordered pairs. So a relation is a set of ordered pairs. So what we're going to talk about in this particular section is we're going to talk about the concept of inverses. In particular, the first thing we're going to talk about is an inverse relation. Okay? So if this is my original relation, we are going to find the inverse relation. An inverse relation is a relationship that takes the outputs from the original relation back to the inputs In other words, it takes the domain from the original and makes it the range of the inverse. It takes the range of the original and makes it the domain of the inverse. So it takes the outputs back to the inputs, the output back to the input. So the new inverse relation would be 4 back to -2, 2 back to 0. In other words, it's kind of like if you took -2 and you plugged it in and got 4, and then you reversed the process, you plugged 4 back in, you got -2. That's what an inverse is. Basically, though, look at what's happening. Essentially, what have we done? We have just taken the x's and the y's and done what? That's right, I heard you. You just switched the x and the y. You switched the inputs and the outputs. You switched the domain and the range. Because that is essentially what happens when you take and you find an inverse relation. So, now what we're going to do is look at what that does on the graph. So we're going to go down here, we're going to graph. So we're going to take -2, 4. We're going to graph that point, left 2 and up 4. Let me cover this up here. Sorry. 0, 2. 1, 1. 3, -4. Hopefully, now that you look at those points, you can tell we're not really graphing any type of specific pattern. It's not a function as far as we know functions like linear functions and cubics and things like that. But it is a function if you think about that vertical line test that we talked about. Each input only has one output. But this is just a small example to get us started. So this is my relation. It's just a set of ordered pairs, a set of points, inputs and outputs. Now let's go over here and let's graph our inverse. So our inverse is 4, -2, 2, 0, 1, 1. Notice something about that point there. That's important to notice. The x and the y have been switched from the original, but they're the same, aren't they? And -4, 3. Now, does anybody notice anything about these two graphs? It's probably kind of hard to tell from here. So let me put them on the same graph together. -4, 3. 1, 1. 2, 0. And then 4, -2. Do you notice anything now? Let me put a little edge around the outside of this one so you realize it's a blue point too. There is a pattern that you should notice. And what that pattern is anytime you switch the x's and y's, if you draw a line right up through the middle right here, this line right here is the line y equals x line. It's a real simple line. This is a mirror image across here. This is a mirror image across here. This is a mirror image across here. In other words, our original flips all the way across that line. Our original flips all the way across that line. Our original flip, oh, wait a minute. That one didn't change, did it? It's on that y equals x line. If it's on that line, it won't flip. This original flips all the way across here. So what is happening is, every time you take an inverse, you are seeing that the inverse is a reflection across that original y equals x line. And so that's something that you need to know about the graph of an inverse. It is always the reflection of the graph of the original across the line y equals x. You may want to pause that and write that into your notes if you're taking notes of the videos. Now, I know some of you probably aren't taking notes of the videos, but it might be a good idea because that might be something that helps you later on. So, we're going to do that one more time really quickly here. So I'm just going to make up a few points here. We're going to draw a point here, 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 and here. That's just kind of a couple funky little points there. So this point right here is the point -2, 1. Then I've got the point -1, 1. Then I've got the point 0, 2 again, not intentional there, and the point 1, 4. So this is my original relation. Again, a relation is just a set of ordered pairs. Now I'm going to find the inverse relation. So we're going to find the inverse relation. Now what did we figure out up here? What did we notice? To find the inverse relation, what you have is it maps the output values back to the input values. Or in other words, the domain of the inverse is the range of the original. The range of the inverse is the domain of the original. Or, in even simpler terms, we switched the x's and y's. We switched the inputs and outputs. We switched the domain and range. So this first point would be 1, -2. This second point would be 1, -1. The third point would be 2, 0. And the fourth point would be 4, 1. Now, if we graphically look at that, you should notice 1, -2 is a reflection across that middle. 1, -1 is a reflection across that middle. 2, 0 is a reflection across that middle. 4, 1 is a reflection across that middle. It will always give you a reflection across that middle line anytime you take the inverse. And so I've had some people say, oh, it looks like a butterfly, Mr. Harrison. Yeah, sure. Looks like a butterfly if you connected the dots or something, whatever. But what we're saying is that anytime you switch those x's and y's, it will flip across this line. The reason it doesn't flip across this line when you're on the line is because on this line, every x and every y is equal. That is literally the line y equals x. So if you flip the x's and the y's there, they will not change. They will be the same points still. So anything that's on this side, though, flips over to here. It's a mirror image. It's a mirror image. It's a mirror image. But anything on the other side, if it was on this side, it flipped to here. So an inverse relation is taking a original relation, inputs and outputs, and switches the x and y. So now that we've looked at an inverse relation, now we're going to specifically talk about inverse functions. Notice that this particular relation down here at the bottom is a function. Each input has one output. It passes the vertical line test. But notice that the other one, the inverse, is actually not a function because this one, this input right here, has two different outputs. What I mean by that is this x value of 1 has two different y values. That is when we have something that is not a function. So you can actually have a relation that is a function that passes the test, but then take its inverse, and the inverse is not a function. So what we're going to look at is inverse functions, where we actually have some that are functions, and talk about things that we need to think about when we have some that are not linear in particular. So what we're going to take a look at first is how do we actually find an inverse function? And so what I have is y equals 2x minus 4. And I'm not real sure why I put relation there. typo, we're going to find the inverse of this function. So number one, it's y equals 2x minus 4. So I want you to sit and think for just a second. What do you think you would do to find the inverse? Now, some of you might have been thinking in your head, well, I could do like we did on the other page. If I had some points, I could take the points and then I could switch the x and the y, and that would be the inverse points, but that wouldn't be the inverse function. That wouldn't be the inverse equation. That would just be the points. So then I'd have to find the equation of those points. So I'd have to find a bunch of x's and y's for this one, switch the x's and y's for this one, and then find the equation of those new x's and y's. That sounds terrible, Mr. Harrison. Is that what we're really going to have to do? No, it's not. It's actually much easier. If you want to find the inverse of this particular function, what you do essentially is like what you do in the table. You switch the x's and y's. What you do on the graph, you would switch the x's and y's in the points. You switch the x's and y's in the equation. So what I mean by that is, if this is my original function, y equals 2x minus 4, this is my original function. I switch the x and y. Notice what that looks like. I did not change anything about the function. I literally switched the x's and y's. Like I did over here on these tables. I switched the x's and y's. Like I did on these points. I switched the x's and y's. So on the equation, I switched the x and y. Then, if I solve this equation right here for y, I will have a new inverse. It is my inverse of the original. So now what I want you to do is I want you to pause the video real quick and solve this for y. Yes, that's an old technique. Hopefully you tried. Now we take this and we are going to add 4 to get rid of this. That leaves me with 2y equals x plus 4. Then if we want to get rid of the 2 beside the y, we divide by 2. We divide by 2, and that gives me y equals 1 divided by 2 would be 1/2 x. 4 divided by 2 would be 2. There's my new function. Now notice something about this one. If you have a linear function and you take the inverse is still linear. This is still mx plus b. Still x to the first power. It's linear. So when you look at these two functions, they are both functions. They're both linear, but this one is the inverse of the original. Now, you're probably kind of thinking, okay, well, what in the world is the inverse? And an easy, very simplified way to think of it, but not very, very good mathematically, so don't quote me too much on this, is that it's the opposite of what the original is. But it's not quite exactly the opposite. Obviously, we added 4 and then we divided by 2 to get this. But notice it does change the function up a little bit. It's 1/2 x plus 2. It's not really still plus 4. And so that's where you got to be a little careful. It's not exactly the opposite. So it is an inverse because it takes the original domain, gave us the range. It takes the original range back to the domain. So if you were to plug in the original y values from this function into here, you would get the x values from the original. Now, for our purposes, most of the time we're going to just have to know how to find an inverse. I do want to warn you ahead of time that sometimes your function will be written with that function notation like we talked about, f of x equals 2x minus 4. But you can still switch this x and this y, because remember, f of x is just a fancy way to write y. You can still switch it just like we did when we found the inverse here. Then we do all the work like we did before, and we get 1/2 x plus 2. What I also want to warn you about, though, is this right here, and this is important for your notes. If you see a little -1 right here above the f, that means f inverse. That means it is the inverse of the original at the top up here. So it is the inverse of f of x. And I apologize a little bit about my crazy looking f there. So, you know me and my handwriting, right? So this is how you find the inverse of a function. You switch the x and y, much like we did in the table, much like we did in the graph, and you solve it for y, and it gives you a new function. What I also want to point out is that if you took the original y equals 2x minus 4, and I'm going to come over here and I'm just going to kind of sketch this. 2x minus 4 would be down over here at -4 for your y-intercept, your big in an amount, and then you would move up 2 over 1. Yeah, you thought you were done with that, didn't you? If you graph that line, we get a line that goes up through here like this, y equals 2x minus 4. If you were to do 1/2 x plus 2, 1/2 x plus 2 begins at plus 2 and then moves up 1 over 2. You're going to end up, sorry, it's a little bit off even though I'm just trying to sketch it. You'll end up with a line that goes across like this. And what you'll notice is, like I said, this will reflect across that line right up through the middle, y equals x. I'm sorry for not being able to get that very straight. All right, so what I want you to do is I want you now to find the inverse of this function. So pause the video here and find the inverse. All right, remember, to find the inverse, what we're going to do is we're going to switch the x and y. Now again, remember that's just a fancy way to write y when you have that f of x. So you can switch this x and y right here, and then we solve this for y. So we add 3 to this side. That's going to be x plus 3. Now how would I get rid of 1/3 in front of the y? I multiply by 3. So if I multiply by 3, here's where you're going to have to be careful. You have to remember what to do. You have to multiply both sides completely by 3. It's going to cancel out the 1/3 here. It's going to give me 3 times x and 3 times 3, which would be 9. 3x plus 9. Now, if you look at this right here, this is the inverse of the original function. Another way that I can write that in alignment with that f of x is to do f with a little -1. That's the same thing as saying f inverse, or the inverse of f. Again, I'll point out that if you were to graph 1/3 x minus 3, 1/3 x minus 3 is going to go up across the graph like this, essentially. And then if you were to graph this 3x plus 9, 3x plus 9 is going to be a fairly steep line coming down this way. And Mr. Harrison is not really good at drawing straight lines, is he? He kind of sucks at it. Sorry, I shouldn't say sucks, I guess, on the video. If you look at that, it would be a reflection across that line, y equals x always. So the next thing we're going to look at is we're going to look at what happens if you take the inverse of a non-linear function. So we're going to go over here and we're going to look at, let's say, f of x is equal to, well, let's go simple on this first one, x squared minus 4. And we want to take the inverse, or find the inverse of this non-linear function. All right, so what I want you to do is I want you to try to use the same techniques that we did a minute ago. Switch the x and y and see if you can solve for y to find the inverse. Pause the video and try it. All right, so if we switch the x and y, just like we did before, notice that I didn't switch the squared. I switched the x and the y, and that's it. And so that's where some of you probably messed up on this one. And that's okay. I was getting you to try it and see how you did. So you literally switch the x and the y. You don't switch anything else, not even the squared. So now how would I solve this for y? First, I would add 4 to this side. So it's going to be x plus 4. And then I would take the square root. If I take the square root, just like I normally do, I have to remember to put the plus or minus. So it's plus or minus the square root of x plus 4. So if you were to think about that, that would be the inverse. Now the plus or minus, though, is going to cause an issue when we think about it actually as an inverse function. So it's going to cause an issue with this if I'm finding the actual inverse function. Here's why. If you want to find the inverse, remember, like I said, you take the original, x squared minus 4 would be a quadratic graph that has been moved down 4 spaces. It's been a little while since we graphed these, but it'd be a parabola that's down here at negative 4. If you take that graph and you flip it across that middle line, y equals x, what are you going to notice? Well, if we look at the function, it's a square root of x plus 4. Remember that plus 4 moves it to the left 4 spaces like we did in graphing the other day. It's actually going to be a point that's reflected over here for my new inverse. So it's going to be right over here. And then it's going to be opening like a parabola, but it's going to be sideways because this thing has been reflected all the way across. Now, I know I don't have a very, very pretty graph here, but when you reflect it across that line, it would switch it completely across, and so it is going to be a radical, the top half being the plus part, the bottom half being the minus part, the plus or minus. Here's the issue. That new thing that you just drew is not a function. The vertical line would hit it twice. So that is not a function. So to truly be an inverse function, what you would actually have to do is limit part of this graph here, meaning your original could not be the entire graph of the parabola. That means that you would have to say we're finding the inverse only if x is greater than or equal to 0. That means only the right-hand side of that original parabola. Then when it flips, it would be this part, the positive part. Because what happens when you switch x and y is that would take away this negative and be just the positive root, because the y values would now be bigger than or equal to 0. Because when you switch x and y, you also switch the domain and the range. So if this is the domain, let me go here. If this is the domain of the original, it's now going to be the range of my final. So it's going to be greater than or equal to 0 for y. Now, that's a lot of information there. You don't typically have to go through and figure all that out on your own. But typically you're going to see, and in your homework problems you'll see this, the original is restricted on the domain because you're trying to find an inverse that is actually a function. If you don't restrict this domain of the parabola, if you do both sides of the parabola, your answer will not be a function. It's still an inverse, but it's not an actual function because it doesn't pass the vertical line test. Okay? So it's not a bad thing if it's not a function. It just means that you could not go through and then do some of the same things that we normally do with functions because it doesn't fall into that category. So what I'm going to do is I'm going to give you another one that is a non-linear function to attempt to find the inverse. Alrighty. So I'm going to give you the original f of x here is the cube root. I'll say here the cube root of x plus 2. And so then I want you to find the inverse. So find the inverse. Pause the video here and you can go through and actually try it first before I go through the answer. So just like all the other ones, we found the inverse. We switch the x and the y. So we switch them on the paper, literally, their places. And then we solve for y. Now, if you'll notice, this one is a cube root around all this stuff. This goes back to earlier in the chapter when we solved with radical equations. How do we get rid of a cube root? We cube both sides. So I'm going to cube both sides. If I do that, what does the cube root do? It basically disappears. On the left-hand side, x cubed is literally x cubed. And then I subtract the 2 over, so this will be x cubed minus 2. This would be my inverse function. And there's nothing weird happening there like we had with the plus or minus with the square root. So this is actually the inverse of this one. And guys, we kind of talked about this before a little bit anyways, but a cube root graph, remember x plus 2 would mean it moves to the left 2 spaces. So you'd have that graph that goes up through here, like we've done before when we graphed those particular functions that are cube roots. You can go back and review that if you need to. There's another graphing video. And then the inverse would be x cubed minus 2. That would be down 2 spaces. That would be a graph that comes across here like this. And it's down 2 spaces, and then it goes up like this. Again, notice it's a inverse. And every single time I find an inverse, it will flip across that line. It's a reflection. But a cube root, the inverse is a cubic function. A square root, the inverse is a square. So that's what we have talked about when we solve equations, is basically the opposite of a cube root is cubing it. But it works the same way when you think about the actual function itself. Notice also on this one that the domain and the range for both of these would be all real numbers, just like it was in the original. Cube root was all real numbers for both of them. The domain and range of this one would be all real numbers because it touches every x value and every y value. So does the inverse. It touches every x value and every y value. Notice also that the inverse of the cube root is a function also. And so one of the last things you'll see when we talk about is that a function has an inverse that is not a function. Sometimes that happens, like the squared function over here. If you don't restrict it, then it's going to be the top and the bottom, and that is not a function. So if you don't restrict the original, you're going to have sometimes a function that has an inverse that is not a function. The quickest way to tell this is by looking at the original function's graph. So think about that parabola we just did just a minute ago. If this is the original function, okay, I'm going to draw a parabola. The inverse of that, let's use black for the axis again. The inverse of that would switch the x's and y's. It would be a parabola turned sideways. Golly, can't get the colors to change here. Parabola turned sideways this way because it is a reflection. But notice the inverse is not a function because of the vertical line test. Well, look at the original. How would you be able to tell by looking at the original that the inverse over here is not going to be a function? Notice what I said there. The original is a function. But how can I tell by looking at this original that the inverse over here is not going to be a function? I hope somebody said it. If you do a horizontal line on the original function, it will tell you if the inverse is a function. Notice what I said there. I'm going to say it again. The vertical line test tests to see if something is a function. The horizontal line test will test to see if the inverse is a function. So if you have a function that looks like a parabola like this, and a horizontal line hits it twice, When you take the inverse, the vertical line is going to hit it. So that means the inverse would not be a function. So let's say it one more time for those in the back. If you have a function that's hit by a horizontal line twice, the inverse would not be a function. So here's a little better example of that picture. If you look at y equals x squared, and then you switch those x's and y's. Instead of having negative 2, 4, you got 4, negative 2. This one flips across here. This one stays there. This one stays there. 2, 4 is 4, 2. You flip it across. That's the inverse. The inverse would be a plus or minus square root. Notice the inverse is not a function because it doesn't pass the horizontal line test. But for cubes and cubic roots, you will notice that that is not true. The original, this x cubed function right here, does not get hit by a horizontal line twice. So that means the inverse is still going to be a function. So the horizontal line test tells you if the inverse is a function. Not the original, the inverse. All right, guys, we got a couple more things and we'll be done with inverses. The first is that when you are looking at a function that models real life values, let me give you an example of that you probably are familiar with from science class. If you are trying to find the temperature in Fahrenheit, you take 9/5 times the Celsius temperature plus 32. And that is the formula for Fahrenheit. That function is a linear function. If you look at it, it's y equals mx plus b, just like other linear functions that we've looked at. It's just using f and c instead of y and x. But the problem is, if you wanted to find the inverse of this formula, if you switch the f and the c in the problem, you just screwed up the whole thing. Because what you have now is you have a function where you've switched the variables. You switched actual Fahrenheit temperatures in Celsius, and those are not interchangeable. So in a real life context, whenever you are looking at taking and finding the inverse of some kind of real life function like the Fahrenheit and Celsius problem we have here, let me just go ahead and I'll just rewrite it on the next page. If you are trying to find the inverse of that formula, you have to make sure that you actually leave the variables as f and c and just solve this for c. Essentially what you're doing is you're just solving for the other variable. It's the same thing as finding the inverse. We just don't actually switch the variables because they actually represent two real world values that you can't interchange. So if you were to solve this for c, you would subtract 32 from both sides first. That would be f minus 32 equals 9/5 c, because these cancel. Then you would get rid of the 9/5 by either dividing by 9/5, or, my personal opinion, I think the easier way to do it, is to multiply that by the reciprocal. To multiply by 5 over 9. And then you can multiply by 5 over 9 on this side. What that does is that cancels out the 9/5, leaves me with c equals. And then on the left-hand side, you have 5/9 times this f minus 32. And I'm okay with you leaving that f minus 32 in parentheses and not actually distributing the 5/9, because that's a pretty ugly fraction. But this would be a new formula for Celsius, but it is still the inverse of the original Fahrenheit problem. Just like we found the inverse when we switched the x and y in those other problems that were either nonlinear or linear, and we were trying to find the inverse. It's the same concept, you just don't actually switch the f and the c. So be careful with that when you're looking at the real world problems. The last thing I want to go over with you is how do you verify if something is truly an inverse of another function. The way to verify it, if you are looking at a table or a graph, is to look and see, are the x's and y's switched? Are the x's and y's switched? If they are, it is an inverse. If you look at the graphs, you can look at the x's and y's and the points and see if they're switched. But you can also look and see if it's a reflection across the y equals x line. But with an actual equation, with an actual function, it's a little bit harder to tell sometimes if you truly have inverses of each other. And so what we want to do is we want to be able to see if these two functions are inverses of each other. So if they are inverses of each other, there is a couple of different ways that we can actually do this. Let's see if I can get over here to the correct page here. I'll cover that up real quick. One way is to actually find the inverse. So one way to see if two things are inverses of each other is to actually find the inverse. Do all the switching of the x's and the y's and solve for y. The other way that you can check and see if two functions are inverses of each other is if you have f of x is 2x minus 4, and let's say g of x is this other function 1/2 x plus 2, and you wanted to know, are those two truly inverses of each other? Yes, you can still just find the inverse and see if it matches, but there's another way using what we did last class or last lesson of using the composition. In inverses, if you plug in an inverse into another inverse of itself, it will always give you x. It works both ways, meaning if you do f of g of x or g of f of x, it will always give you x because inverses are always going to cancel each other out. Let me show you what I mean by actually plugging this one in. If I do f of g of x, if I take 2x minus 4, but instead of x, I plug in the whole function for g, 1/2 x plus 2, you'll notice really quickly if this is going to work or not. You do 2 times 1/2 x, that gives you x. 2 times 2 is 4. If you subtract those 4's, you get x. G of f of x should always work the same way if they are inverses. So if you take 1/2 x plus 2, but instead of plugging in x, you plug in the actual function f of x, 2x minus 4. If you do 1/2 times 2x, that's x. 1/2 times negative 4 is negative 2. The 2's cancel, you get x. In inverses, the f of g of x and g of f of x will always cancel out to just x. If it doesn't, they're not inverses. So there's multiple ways you can check and see if things are inverses of each other. You can look at the points and see if the x's and the y's switch. You can look at the graph and see if the points, the x's and the y's switch. You can look and see if it's a reflection across that line. You can also look and see if you actually find the inverse, if it gives you the other function, or you can plug them into each other. If you do that composition of functions, it'll always cancel out to x if they are inverses. Now what that does, one little quick thing, one last thing I'll give you, is every once in a while, I've seen this on the SAT several times. In fact, when I took it, it was on the SAT. If you have f of f inverse of 3, notice that it says you are plugging an inverse into the original function. Inverses and original functions always cancel out to just x. But there's not an x there, Mr. Harrison. There's a 3. Exactly. It just cancels out to 3. And so it's a nice little easy, quick question, and they're just checking to see if you understand the concept of inverses. All right, so your homework is going to be in your textbook here. If I can get this to highlight properly, page 287. And it's not going to let me. Let's see if I can do it without using the tablet. There's 287. That's your homework. And I will post the PDF documents for your homework on Schoology. Remember, those will be on the Schoology page where you go to the Algebra 2 Materials tab. If you go underneath there, underneath Materials, you go down to the bottom, I'll have a little folder here that has inverse functions, and then I'll have the actual PDFs inside there, as well as this lesson. I will post this lesson, and then I will also put the assignment into Schoology itself. Then you will finally, like I said, also have the textbook, the online textbook to choose from. If you click on the online textbook, you'll be able to look right in the middle of the page here and see your assignment. I'm saying this about 13 times because I've answered about 40 or 50 questions from different people who didn't pay attention to the videos. So make sure you pay attention and listen. All right, guys. Hope you're staying safe out there.